To train a machine to recognize objects in the real world, you have to show it the real world. In 2012, that meant feeding a model the ImageNet dataset, 1.2 million high-resolution images hand-labeled into 1,000 highly specific categories. Before this point, researchers approached large-scale image recognition by manually writing algorithms to look for specific shapes and edges, using handcrafted feature extractors like SIFT. But these human-engineered methods hit a mathematical limit. The error rate for machine vision stalled, hovering persistently around 26%. This chart shows the error rates at the 2012 ImageNet Large-Scale Visual Recognition Challenge. The benchmark set by traditional models sits at 26.2%. But a single entry that year drove the top 5 error rate down to 15.3%. That winning entry was designed by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton from the University of Toronto. Their architecture, which would come to be known as AlexNet, was a deep convolutional neural network. Closing that nearly 11% gap proved that a neural network could learn visual features directly from raw pixels more effectively than human engineers could hand-code them. Mapping millions of chaotic, real-world pixels to thousands of distinct labels requires an immense learning capacity. To achieve that capacity, the Toronto team designed an exceptionally deep network. It contained 8 learned layers, 5 convolutional and 3 fully connected, housing 650,000 neurons and over 60 million individual parameters. Processing a network of that size requires massive computational power. In 2012, the researchers relied on the NVIDIA GTX 580 GPU. The strict physical constraint of this hardware was that it possessed only 3 gigabytes of onboard memory. Training 60 million parameters on a single GPU creates a severe mathematical bottleneck. If the model is too big, it instantly runs out of memory. If you scale it down and feed it all that data without strict regularization, it overfits, memorizing the training images instead of learning how to actually see. The 2012 paper overcame this paradox through the structural engineering required to force 60 million parameters through a 3 gigabyte memory limit. The first major hurdle is chronological. Calculating the gradients for 60 million parameters requires an enormous amount of time. Standard neural networks modeled their outputs using saturating nonlinearities, like the tan or sigmoid functions. As inputs grow larger or smaller, these functions flatten out. Their gradients approach zero, which slows down the learning process during gradient descent. To bypass this, the team swapped those equations for the Rectified Linear Unit, or ReLU. It operates on a simpler mathematical rule. F of x equals the maximum of 0, or x. It does not saturate. This chart illustrates the difference in training speed. Using the CIFAR-10 dataset, the researchers measured how many iterations it took for a 4-layer convolutional network to reach a 25% error rate. The dashed line shows the network with traditional saturating neurons, slowly trending downward. The solid line is the exact same network equipped with ReLUs. It hits the target error rate 6 times faster. Without this mathematical acceleration, experimenting iteratively with a network large enough to process the ImageNet dataset would have been practically impossible. Even with ReLUs speeding up the math, the memory limit remained. Feeding over 1 million high-resolution images, downsampled to 256 by 256 pixels, into the model instantly overloads the 3 gigabytes of VRAM on a single GTX 580. The researchers solved this by splitting the network directly in half. They assigned exactly half of the feature kernels and neurons to one GPU and half to a second GPU. Because writing to another GPU's memory is slow, the parallel hardware had to operate independently. For the first 2 convolutional layers, the GPUs do not communicate at all. Data moves strictly forward within its own lane. They force the system to synchronize only at specific choke points. The kernels in Layer 3 take inputs from all the kernel maps in Layer 2 across both GPUs. By Layer 4, the columns are isolated again. This connectivity pattern fit the model in memory and reduced the top 1 error rate by 1.7% compared to a half-size network trained on one card. Using ReLUs solved the compute time, but it introduced a new risk. Because ReLUs don't require input normalization, large positive inputs can create massive activation spikes that overwhelm the network. To keep these spikes in check, the network applies local response normalization. Inspired by lateral inhibition in real biological neurons, This technique forces the outputs of adjacent feature maps to compete, suppressing weak activities and highlighting strong ones. They also adjusted how the network summarizes data. In traditional CNNs, pooling layers summarize groups of neurons in distinct, separate blocks. Here, the network uses a 3x3 pooling window, but steps it forward by only 2 pixels at a time. The windows overlapped. These localized tweaks forced the extracted visual features to compete against each other and pool together more densely, making it harder for the model to overfit. The most severe risk of overfitting actually sat at the very end of the network. The final 3 fully connected layers consist of over 4,000 neurons each, containing the vast majority of the model's 60 million parameters. With density like this, the network can develop complex co-adaptations. Instead of identifying robust features, a neuron will lazily rely on specific other neurons to memorize exact training images. To forcibly break these dependencies, the team implemented a regularization technique called dropout. During training, dropout sets the output of exactly 50. It cannot rely on any single neuron always being there, so it is forced to learn robust, redundant visual features that survive even when half the pathways vanish. After roughly 90 passes through the 1.2 million images, the network finalized its weights. We can examine the very first convolutional layer to see exactly what the model learned to look for. These are the 96 kernels learned from the raw pixels. Half of them detect frequency and orientation, high contrast edges and lines. The other half identify specific diffuse color blobs. But the distribution of these kernels reveals an unintended side effect of splitting the architecture across 2 separate pieces of hardware. The features on GPU 1 are almost entirely black and white and color agnostic. Meanwhile, the kernels on GPU 2 dedicated themselves almost entirely to processing color-specific information. No programmer instructed the model to process shape and color separately. The network organically evolved distinct visual pathways as a byproduct of the hardware restrictions. To prove the network learned high-level semantic meaning and wasn't just performing advanced pixel matching, we evaluate its predictions on images it has never seen. This output shows the model's top 5 predictions for test images. It accurately identifies the subject, like this mite, even when the object is tiny and pushed to the edge of the frame. When dealing with photographic ambiguity, its secondary guesses remain logically sound. A Dalmatian with cherries yields labels for grapes and elderberries. A Madagascar cat prompts alternative primate and feline species. The model is grouping concepts by semantic category. We can verify this deeper in the network. This column shows 5 query test images. By measuring the Euclidean distance of the feature vectors in the network's final hidden layer, we can see which images the model considers to be structurally identical. These are the 6 closest training images retrieved for each query. The elephants and dogs appear in completely different poses, against different backgrounds, with different lighting. These results show that the network is classifying based on deep semantic features, reaching an invariance to the specific poses, backgrounds, and pixel-level arrangements of the query. The depth was indispensable. Removing even a single convolutional layer permanently drops performance by 2%. This balanced architecture provided the proof that purely supervised deep learning could solve large-scale visual recognition.